In the previous lectures, we've looked at the compromises and the performance limitations you can apply to instrumentation amplifiers. In this lecture, we will look at a real application and one that will be very relevant for your design challenge. Here we have a classic application for an instrumentation amplifier. We have a load cell which consists of 4 resistors of nominally identical values. We'll talk about R4 in a second. So the output voltage appearing here is the supply voltage times the difference of the voltage appearing here and appearing here. And typically in a bridge amplifier or a Wheatstone bridge, R1 is equal to R2 and held constant, and R3 nominally equals R4, but R4 also has a factor delta, which in the case of perhaps a load cell varies according to the load applied to the load cell. So our output voltage equals 1 over 2 plus delta minus 1 over 2. Well, we know from the binomial expansion that 1 over 1 plus delta can be approximated as 1 minus delta plus delta squared minus delta cubed plus delta to the 4. So let's apply this and analyze our equation. So here we have our equation from the previous slide. We are going to expand out the first 2 terms from the binomial expansion, and it equals approximately minus Vs times delta divided by 4. Given that that's the output signal from a Wheatstone bridge, the limit on sensitivity is going to be the common mode rejection ratio of the instrumentation amplifier that you attach to that cell. And working through the maths and working at the limit of sensitivity, which in other words is the minimum detectable change in delta, or delta min, we can approximate that to delta min equals 2 divided by the common mode rejection ratio of the instrumentation amplifier. Let's look at another example, and here we have a magnetic compass chip. It's a Honeywell HMC 1002 and it's set up as a Wheatstone bridge. In this case here, we have with 0 Gauss or no magnetic influence, these 2 resistors here equal these 2 resistors here, and all 4 resistors will be equal with no magnetic field. The specification we've got is the output voltage gives 12.5 millivolts output for every Gauss of magnetic flux. And the common mode voltage, because we're supplying it with 5 volts, will be 2.5 volts. In this example, the bridge resistance, in other words, there's 4 per bridge, is 850 ohms, and the full scale magnetic flux across the unit will be plus or minus 2 Gauss. Let's define the specification for this circuit then. So we want an output signal which is equal to 1 volt per Gauss. And we're going to assume a total additive error equal to 0.0175 Gauss. And just as a reference point, the magnetic flux around the Earth is around 0.4 Gauss. So we're a lot better than that. This gives us a total referred to input voltage error of about 218 microvolts. And you can calculate that out by the sensitivity of the unit, which is 12.5 millivolts per Gauss, multiplied by the total additive error, which is 0.0175 Gauss. Let's make up our naive design, and for an output voltage of 1 volt per Gauss, we need a gain of 80 times, which is 1 volt divided by 12.5 millivolts. So we've come up with this circuit here, and as a starting point we're going to assume using TL071 op amps because they're the lowest cost amp amps. Let's look at all the errors around this circuit. We've got bias currents on the op amps, we've got offset currents on the op amps, and we've also got offset voltages. So this is a very complex circuit to analyze. Is there a way we can simplify it? Let's consider what the application is and consider what we're trying to do. So first thing we can do is we know the gain of the input stage is large, so any errors due to the different stage for gain can probably be ignored because they are 40 times less important. The bias currents of A1 and A2 we know to be different, but we also know that the offset current cannot be larger than the bias current. So we're going to ignore it, and we're also going to assume there is no matching of input currents for A1 and A2 because they could be two separate and discrete amplifiers. The third point is we will reduce the feedback, the impedance of the feedback network around A1 and A2 so that it is less than the impedance of the bridge that's supplying the signal. This means that we only need to consider the problem of IB plus, and IB minus will disappear because of the low impedance of the feedback network. Let's draw our circuit now with these assumptions in place. Well, that's considerably better because what we've done is we've managed to assume that these offsets are very small. Because this is a low value here, we're going to ignore the offset value here, and we've also changed these two resistor values here 10 times lower because RB has been reduced by 10 times. In the difference stage, we've said that all of these effects here are 40 times smaller, so for this analysis we can ignore them. And similarly, the offset voltage and the common mode input signal into the amplifier can also be ignored because it's 40 times lower. So that leaves us with the common mode rejection of the two amplifiers A1 and A2, and also the offset voltage of the two amplifiers A1 and A2. What we want to do now is look at all the sources of error with this naive circuit design. We've got a total error budget of 218 microvolts, which we calculated out early. And looking at our TL071, our offset voltage is 10 millivolts. We have two amplifiers, so we have a worst case offset voltage of 20 millivolts. That's not good news, but let's continue and do the analysis. Our bias current is 850 ohms times 0.2 nanoamps, so it's 170 nanovolts. That sounds quite good. Our op-amp common mode rejection ratio is 2.5 volts, which is the mid-rail of the bridge, divided by the 70 dB common mode rejection ratio of the amplifier, which gives us an op-amp common mode rejection ratio of about 790 microvolts. And finally, we have our resistor matching. We've got 2.5 volts times 2%, which if we assume 1% resistors, is 2.5 volts times 2%, divided by 80, gives us about 625 microvolts. So we've got a few things here we really need to look at to improve our circuit design. The first thing we can do straight away is say that the 1% resistors, which we're going to give 625 microvolts error, we will move them to 0.1% resistors. And that gives us a resistor budget of about 62.5 microvolts. This means that we have about 150 microvolts left for the rest of the amplifier error budget. It's clear that the TL071C is not good enough to do this application, but can we find a better op-amp? Writing down the figure of merit, and we've done this in previous lectures, our figure of merit for this circuit is 2 times the offset voltage, plus the bridge resistance times the bias current, plus 2.5 volts divided by the common mode rejection ratio. Plugging into our well-known op-amp table here and looking at the numbers, we find that the amplifier that meets the requirement of better than 150 microvolts is the OP177GP, and it's the lowest cost component that meets the spec. So now we can look at our final magnetic amplifier circuit. We have our 5 volt supply over here. We've got our HMC1002 here, and now we are using 3 times an OP177. The matching of these resistors here is not critical because it only affects the overall gain, and we've decided to go for 0.1% resistors around the difference amplifier in order for us to get the common mode rejection ratio we require. Starting from a very high level specification, we've done the analysis, we found out that our initial naive design and our initial choice of op-amp was not good enough. We identified how we had to improve the op-amp performance, and we carried out a figure of merit analysis for that op-amp. We eventually applied that to the end circuit, and we found a circuit that met the requirements and met the specification that was demanded. Thank you very much.